All of you can see the content on the screen, guys. Is it visible? All of you. The content is visible.
Sir.
Ah, content is visible on the screen. Whatever I'm sharing.
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. Before that, just I'll give some brief introduction about the refrigeration cycle. Okay. So refrigeration is the process of maintaining the temperature of the system below the atmospheric temperature. How you are going to achieve that temperature is by means of continuously extracting the heat from the system and maintaining that temperature within the system itself. That is called as refrigeration. Okay, so the process of reducing temperature below the atmospheric temperature is called as refrigeration. Okay, as you know, the refrigeration plays a very important role in all aspects of our life, like in case of storage of raw fruits, vegetables, fish, everything. We are going to use the refrigeration, storage of dairy products. Okay, the production and cooling of fruit juices, processing and distribution of frozen food. These are the few applications of refrigeration. Okay, so before going to your actual experiment, just I'm going to explain what are the parts of your vapor compression refrigeration system. Okay, so once you understand this system, then it is very easy to conduct one more experiment, that is the air conditioning. Air conditioning is also a part of refrigeration system. And what is the difference between refrigeration and air conditioning is that in case of refrigeration, we are going to reduce the temperature below the atmospheric temperature. So on the other hand, in case of air conditioning, not only controlling the temperature, meantime we can control the humidity, that is the moisture content, then cleanliness of air, then flow of air within the confined space. So these are the additional things come across the air conditioning. Okay, so that is the difference between refrigeration and air conditioning. In case of air refrigeration, only reducing the temperature below the surrounding temperature. So in case of air conditioning, not only controlling the temperature according to our requirements, we can control the humidity, that is moisture content, next cleanliness of air, and also the particular flow of air within the confined space. Okay, now what you are seeing on the screen is your the vapor compression refrigeration system. Okay, so a vapor compression refrigeration system mainly consisting of four parts. You remember, one is evaporator, what you can see on the top. Next we are having the compressor, next we are having condenser, and fourth one is expansion valve or throttle valve. Okay, so first one is evaporator. It is placed in the cabinet of refrigerator. Next, compressor is kept at the bottom of the compressor. Next, condenser is kept at the behind position of your refrigerator. And one more is there, expansion valve. It is a valve which connects between evaporator and condenser. So these are the four basic parts of vapor compression refrigeration system. Okay, mainly there are two types of a refrigeration system. One is vapor compression and one is vapor absorption refrigeration system. Okay, so we are going to mainly deal with the VCR. Okay, before going to do the experiment, just I'm going to explain how the process works. Okay, in case of refrigeration, so we are going to use a carrier substance called as refrigerant. Is a substance which is used in the refrigeration system. Okay, you know the various refrigerants used in the system, mainly ammonia, carbon dioxide. Next we are having freon group of refrigerants, and then modern refrigerants. So whatever refrigerant we are using in our laboratories, R12 or R22, that is freon 12 or freon 22. It is a carrier substance which undergoes the change of phase from liquid to vapor in evaporator and from vapor to liquid in the condenser. Okay, that is a function of refrigerant. Okay, already studied desirable properties of refrigerant, like it should be non-toxic, it should be non-flammable, it should have good chemical stability, it should be easily available, it should be eco-friendly, like that. Okay, these are the desirable properties of refrigerant. Okay, first I'll explain the working principle of vapor compression refrigeration system. First, uh, the low pressure and low temperature liquid refrigerant. Okay, you see we are going to start with the evaporator. First in the cycle, we are going to start with low pressure and low temperature liquid refrigerant enters into the evaporator. As I said, evaporator is a coil which is placed in the cabinet of the refrigerator. When it enters into the cabinet, it absorbs the heat from the uh, cabinet or given space. Okay, when it absorbs the heat from the cabinet or given space, then there will be a change in phase from liquid to vapor. That liquid refrigerant converted into the vapor refrigerant when it enters into the evaporator coil. Okay, so now condition of refrigerant is vapor refrigerant, which is at low temperature and low pressure state. Okay, so the next, low pressure and low temperature vapor refrigerant from the evaporator enters into your compressor. Already you know the function of the compressor to increase the pressure and temperature of the working substance. Okay. Next, we are having the high pressure and high temperature vapor refrigerant then enters into the condenser coil. Condenser coils always kept at the back of the fridge or refrigerator. So in case of condenser, there will be change in phase from vapor to liquid. When it enters into the condenser, the vapor refrigerant gives away the heat to the surroundings. Then temperature decreases. So as the temperature decreases, there will be a change in phase from vapor to liquid. That is called as condensation. The change in phase from liquid to vapor is called as evaporation. Okay, so the high pressure and high temperature. Okay, when low pressure low temperature vapor refrigerant enters into the compressor, both pressure and temperature increases. That enters into the condenser coil. Okay, so where it gives away heat to the surroundings. Okay, next, now condition of the refrigerant is the high pressure, there is no change in pressure but the temperature decreases. The condition of refrigerant is high pressure and low temperature liquid refrigerant after passing through the condenser. But whatever the pressure, suppose you pass the same high pressure liquid refrigerant into the evaporator, will not get the good efficiency. So we have to reduce the pressure of liquid refrigerant to the practical limits. Okay, that's why we are having a valve called as expansion valve or throttle valve. Already you know the expansion process. Expansion process is one in which there will be decrease in the pressure. Okay, so this high pressure low temperature liquid refrigerant then enters into the expansion valve. The main function of the expansion valve is to regulate the flow of liquid refrigerant from condenser to evaporator, and also it decreases the pressure of liquid refrigerant. These are the two functions of expansion valve. Okay, first it regulates or controls the flow of liquid refrigerant from condenser to evaporator for next cycle of operation, and also it reduces the pressure of liquid refrigerant to the practical limit. Okay, so next, for after passing through the expansion valve, the pressure of the refrigerant gets reduced. Okay, for next cycle of operation, the low pressure and low temperature liquid refrigerant enters into the evaporator coil, then absorbs the heat. Like that, the cycle will continue. Always you have to remember these are the four basic parts in the vapor compression refrigeration system. Okay, one is evaporator kept in the cabinet. Second one is compressor kept. It is placed at the bottom of the refrigeration system. Condenser coil placed at the backside of the uh, refrigeration system. Then expansion valve. It is a link between evaporator coil and condenser coil. This is how the vapor compression refrigeration system works. Okay. Now this is your actual experiment number 11 serial number in your lab manual. Our aim is to find out the COP, that is coefficient of the performance of refrigeration system. Okay, COP. Okay, already studied efficiency of any engine. Efficiency of any engine is net work done divided by heat supplied. Okay, and in case of refrigeration, we are going to express in terms of COP, coefficient of performance. The formula for coefficient of performance is Q divided by W. The how much amount of the heat is extracted from the system to the work required to do the extraction. That is a formula for COP, that is Q divided by W, the amount of the heat extracted to the amount of work done to do the extraction of the heat. That is a formula. That is our aim, is to find out the refrigeration test rig. Okay, to find out the coefficient of performance of the given refrigeration system. Okay, now the whatever the apparatus required is it consisting of following, that is refrigerant used, then as I said, compressor, condenser. These are the additional device: cooling fan, throttle valve, capillary tube, evaporator, digital pressure indicator to indicate the pressure of the system, temperature indicator, how much temperature changed. Okay, these are the whatever the apparatus used in our lab. Okay, refrigerant, compressor, condenser, capillary tube. And here we are having the two parts. One is throttle valve and capillary tube. Okay, the function is same. Okay, so one time we are opening the throttle valve and closing the capillary tube, and other time we are going to open the capillary tube and closing the throttle valve, but the function is same. We are going to check how much amount of the expansion takes place in throttle valve and how much amount of the expansion takes place in the capillary tube, but function of both the parts are same. Okay, to reduce the pressure to the practical limits. Okay, and a pressure indicator to indicate the pressure of the refrigerant, and temperature indicator. These are the apparatus required in the system. Okay, next procedure I'm going to explain. Okay, first you have to switch on the mains as usual to keep either the throttle valve, you remember, throttle valve or capillary tube open. When the capillary tube is open, the throttle valve should be closed, and vice versa. That's why we're going to conduct the experiment for two times. One is using throttle valve and one is using capillary tube. First time we're going to open the capillary tube open and then closing throttle valve, and in the next set we are going to open throttle valve and closing the capillary tube. So the function is same, throttling process to means expansion process, reducing the pressure to the practical limit. Okay, both the devices have same throttling effect. First one, switch on the main, and either you can use throttle valve or you can use the capillary tube, and then you can change the set of readings. Okay, switch on the motor. Okay, to drive the compressor. Okay, motor is required, so switch on the motor which drives the compressor and cools the condenser. Okay, as you switch on the motor, the cycle starts. Okay, the refrigerant passes through the vapor compression cycle, as I explained how the refrigerant flows in different parts, resulting in the cooling. Okay, next, and you have to wait for 5 minutes. and note down the temperature. There are five temperature readings in the knob: T1, T2, T3, T4, and T5. Okay, so you'll get in the setup, experimental setup, there are five readings, T1 to T5. The T1 indicates the temperature at compressor inlet. Okay, how much temperature is there before entering into the compressor. T2 is the temperature gives the compressor outlet reading. T3 is temperature at condenser. Next, T4 is temperature at evaporator inlet. Okay, the T5 temperature inside the freezer. Okay, so these are the five temperature at compressor inlet, and all are in degrees Celsius. And we are having two pressure readings, P1 and P2. P1 is pressure of compressor in terms of kg force per centimeter square. You remember whatever readings we are getting in our lab is in terms of kg force per centimeter square. After that, using conversion factor, we are going to convert this kg force per centimeter square into a bar or kilopascal, etc. Okay. Next step is you have to note down the power input to the compressor. How much power is required to run the compressor? You have to note down all this temperature. Mainly temperature is most important. Pressures you have to remember. Pressure you have to note down. These are the readings you are going to take: T1 to T5 and P1 and P2 readings. Okay. So once using the measure temperature, pressure, and a power input compressor, then coefficient of the performance and capacity of the refrigeration can be determined. So you are going to take totally seven readings: T1 to T5, P1, and P2. Okay. Now, by knowing the temperatures, pressures, and power input to the compressor, the COP of refrigeration can be calculated. Okay. Now, in this case, before doing the experiment, you should know how to see the pH chart and how to locate the values on the pH. That is most important. Once you understand how to take the values, then only you can calculate the coefficient of performance. Okay, so there are four values you have to calculate. Okay, I'll show one video how to take the H1, H2, H3, and H4 readings. Okay, H1 is enthalpy, and all the values we are going to get from Freon 1 to chart. Okay, suppose if you are using Freon 2 to as a refrigerant, then in that case we are having different chart, that is Freon 2 to chart. So depending upon the refrigerant used in the laboratory, so we have to refer that chart. Okay, that is called Freon 1 to chart: H1, H2, H3, and H4. Okay, so these are the four values you are going to get. Okay, uh, and the formula is coefficient of performance is H1 minus H4 divided by H2 minus H1. Okay, and HP per ton of refrigeration is given by power input to the compressor. As you are finding out the power input to the compressor, you are taking that reading divided by 3.5. That is, 1 ton of refrigeration equals to 3.5 kilowatts. So before that, you should know how to calculate the H1, H2, H3, and H4. Okay, so I'll show the nature of the diagram. Okay, this is the nature of diagram. Okay, now I'll show one video to how to take the values of H1, H2, H3, and H4, and how to calculate the COP. Okay. So guys, are you seeing the video on the contents? Okay, hope you understood how to see the chart. That is, pH chart is most important. Okay, have you seen the
No,
chart?
sir. Hello. See, sir.
Hello, you're not. Tell me.
So I couldn't
Tell
understand
me.
anything, sir.
Huh?
So I couldn't
Not
understand
understood.
anything at all. Sir. No, sir, nothing, sir. There's
At
no
least you have
volume
seen
also,
the.
sir.
No, at least you have. Okay. No, at least you have seen the chart. Nature of chart. Okay.
So I only saw the chart, so if you only show me the chart, I recognize the chart, but I can't do anything
Ah.
in the exam with this, sir.
Okay. Okay, sir. Okay. Okay. And at least you have seen the chart. Nature of chart you have seen, no?
I've
Like.
seen the chart, sir. What you shown on picture, I've seen, sir. That's all I've seen, sir. One calculator and picture, sir.
Oh. Okay. Okay. Just a minute. Okay. Okay, and now I'll explain what is the actual equipment in our lab. Okay, so this is the uh, layout of your VCR. We are having a evaporator. This is evaporator cabinet. Then we are having a compressor. Okay, from the evaporator, it enters into the compressor. Second part. Then we are having condenser. Okay, then we are having this part. What is that called? Capillary or a tube or expansion wall. Okay, this is your the flow diagram of VCR. Okay, evaporator, compressor, and this is condenser and capillary tube or your expansion wall. And this one in the panel we are having the pressure gauges and temperature to indicate the pressure and temperature. Okay, now I'm showing one reading. Okay, so what are the readings are there? I gave the different temperatures, that is T1, T2, T3, T4 and T5. You are going to take the readings P1 and P2. These are the readings you are going to take. Okay, the 5 temperature readings and 2 pressure readings. Okay, so this one is actually conducted in your lab. Okay, so we are getting, these are the values when capillary wall is open and expansion wall kept closed. Okay, in the second case, expansion wall is open and capillary wall kept closed. Okay, so these are the 5 temperature readings and 2 pressure readings are there. Okay, now how to calculate is most important thing. Okay, so most this one capillary open, and you remember in case of capillary tube you are this one whatever readings we are getting in terms of inch. Okay, remember that you have to convert in first mm and then from mm into hg and then bar. Okay, so readings what you are getting in our lab, it is in terms of inch. Okay, so that for capillary open we are getting the p1 as minus 5 inch. Pressure you have to express in terms of bar. That 5 inch you convert into mm, that is 5 into 25.4, that is minus 127 mm. We know that 760 mm is nothing but 1 bar, so 127 mm is nothing but your 0.167 bar. Okay, so all the values you are going to express in terms of bar. Okay, and p2 value, so I am showing the calculation for first reading whenever capillary wall is open. Okay, and p2 is 100 psi. Okay, one unit is there, pound per square inch. Okay, that is 100 psi. Once again you have to convert that psi into bar. How to convert means, this is a conversion factor you have to remember. 100 multiplied by 0.0689 into 0.981. So by multiplying this factor you are going to convert psi, pounds per square inch, into bar. Okay, first you see the reading, same set of readings you will get in the lab. Okay, this is actually a conducted experiment in the lab. Okay, so first whatever inch is there, first step is you have to convert that inch into bar. That is minus 5 into 25.4, that you are getting in mm. We know that 760 mm is nothing but 1 bar. So 127 mm is nothing but minus 0.17 bar. Okay. Next we are having, we have to convert. So because we are getting different readings, you have to convert into proper units. 100 psi, that is pound per square inch. That is a British unit. Then you have to convert in SI units by multiplying this factor. You remember this factor, 100 multiplied by 0.0689 into 9.981. So after conversion, so you'll get 6.76 bar. Okay. And we know that you studied the pressure. Absolute pressure is ambient pressure plus your whatever pressure you are getting, that is P1. So absolute pressure is given by ambient pressure is 1 bar minus of 0.167. So you are getting the pressure as 0.833 bar. Okay. Now, so this is your actually pH chart, what you have seen in the diagram. Okay. This is called as your saturation curve. So above saturation curve, we are getting the steam, and below within the saturation curve, we are getting the uh, liquid and vapor region, that is called as wet steam. Okay. That is 1, 2, 3 and 4. Okay. So whatever the temperature it is shown in the diagram. Okay. So whatever explained in the video, that is according to that. So you have to follow that steps, and you have to find out at particular temperature means how much, or pressure. Okay. Pressure P1 is how much you are getting, minus point this one pressure, sorry, pressure is 0.833 we are getting. So we are having constant pressure lines. Okay. This is whatever 0.1 is there, no, you have to take 0.8 value on the chart. All horizontal line represents pressure lines, and all vertical lines are represent your enthalpy lines. Okay. Corresponding to pressure, so at of 0.833 bar, don't take this minus 0.167, you have to add this one. Okay. Absolute pressure is ambient or atmospheric pressure plus P1. Okay. Because we are getting the P1 as negative, it is nothing but your vacuum pressure, we will not get the negative pressure. For that you have to apply this formula, absolute pressure equals to ambient pressure plus P1, that is 1 minus 0.167. Okay. So you are getting 0.833 bar. Okay. You have to locate the value of H1 on the pH chart. The P is your y coordinate, and x coordinate is your enthalpy. Okay. So corresponding to 0.83 bar, so you have to locate 0.1. Okay. And so come downwards, that is 1, that is H1, the vertical line is your H1. Okay. Similarly at pressure 2. Okay. What is the pressure 2? 6.8 bar, like that we are having a 6.8 bar. Okay. So you locate and you see the temperature T2. Okay. You have to see the temperature T2 corresponding to this temperature and pressure. You have to locate 0.2, that is your H2. Okay. So after seeing this one, you have to drag down. Okay. Meantime, you have to locate the temperature and pressure properly on the R12 chart. Okay. So we are having a chart. R12 is a refrigerant used in the refrigeration system. You have to refer that chart only, then only you'll get the correct answer. By knowing the temperature and pressure, we can locate the 0.1, and then by knowing a T2 and a P2, so we are going to locate the temperature T2. This is called as the entropy, the constant entropy line. You have to follow the inclined line in the pH chart. First location of 0.1 is important, then you have to locate 0.2. So you have to follow the constant entropy line. Okay. This is called as the isentropic compression. Okay. Next 2 to 3. Okay. That temperature 3. Here you have to note down this temperature. One is around okay, 22.1 temperature. Okay. So you have to note down point number 3 on this curve. Okay, and then 3 and 4 are same. This is called as isentropic expansion. Okay, next H3 and H4 are same, but you have to locate all the points properly on the HS diagram. Okay. Once you know H1, H2, H3, and H4, you are going to calculate a COP. Okay, here COP is given by H1 minus H4. That is called as Q. That is amount of the heat extracted divided by net work done. Net work done is nothing but your H2 minus H1. Okay, that is your compressor work. Okay, but locating the values 1, 2, 3, 4 is most important. That's why you have to refer that chart. You see the values. Okay, and you have to locate the values. Once you locate the points, then only you can calculate the COP. That is H1 minus H4. That is your evaporator work. That is Q, because amount of the heat added in the evaporation divided by work. Work where happens in case of compressor. That is H2 minus of H1. Okay. So by location, this one we are getting the values of H1 as 320. Here H1 as 320 and H2 as 340. It is greater than H1. H3 and H4 are same. So this is your constant enthalpy line. It is also called as isenthalpic line. Okay. So by substituting the values, we'll get the COP as 3.5. Sorry, this is 3.5 COP will get. And one more calculation you are going to do is HP by ton of refrigeration. HP means here we are going to find out the power. So capillary open, you are going to note down how much power is required to run the compressor. Here in this case 180 second is required. Okay, you have to note down the time 180 second in first case. That is 0.16 whatever you are getting. Whatever COP you are getting is 3.5 and 0.16 kilowatt means this is 750 energy meter constant, 5 revolution of energy meter into 3600 and divided by 150 is what actually we have noted down. Means this much of the time is required to drive the compressor. Okay, this 5 is constant, 5 revolution, 750 energy meter constant into 3600. So you are going to convert in seconds divided by 150 is your time what you are noted down in the experiment. So using this one, power is 0.16 kilowatt. Just you take the ratio 0.16 divided by 3.5. That gives you how much kilowatt per ton of refrigeration is produced. Okay, and similarly we are going to calculate for other set of reading also. That is, whenever expansion valve is open, we are getting two readings, P1 and P2. Okay, and you remember you take the second set of readings. Expansion valve is open and time required is here 98 seconds. Okay, to drive the compressor, and these are the readings, 5 temperature readings and 2 pressure readings. And here you remember in case of expansion valve, the pressure we are getting in PSI, pound per square inch. You have to convert in terms of bar by means of 0.0689. Okay, you remember these are the two important things you have to remember. First inch to mm, next mm to your bar divided by 760, and pounds per square inch to bar means multiply by 0.0689 into 0.981. This is a conversion factor. Okay, like that you have to convert the pounds per square inch. Okay, so P1 here you see 5 psi, pounds per square inch. This is a second set of readings. Whenever expansion valve is open, 5 into 0.0689 into 0.981, you are getting 0.3379 bar. Okay, and P2 is 120 psi. Once again you convert into a conversion factor 8.11 bar. Okay, so we are getting two bars. One is 8.11 bar. Okay, you see this is called as evaporator pressure. Okay, and one is condenser pressure. Okay, P1 and P2. Okay, P1 how much you are getting? P1 here it is 0.3379 bar and P2 is 8.911 bar. Okay, P1 is 0.33 bar and P2 is 8 bar. Condenser pressure is higher than your evaporator pressure. Okay, after calculating that one, so next step is the standard formula, you remember, H1 minus H4 divided by H2 minus H1. Okay, now corresponding to 0.3379 bar and T1, where is the temperature T1? Here in the second case it is 9.5. Corresponding to 9.5 and the pressure, you have to look at the 0.1. Now you take the constant entropy line. This is most important to locate 0.2. Okay, that you have to, what is pressure 2 now? Pressure 2 is, in second case it is 8 bar and temperature 2, okay, is your 63.5 degrees Celsius. Corresponding to P2 and T2, you have to locate 0.2. Okay, next third temperature is your 35 degrees Celsius. Okay, next you take the straight line and then you have to locate the 0.3. Okay, and 3 and 4 you have to locate, get the values of H1, H2, H3 and H4. Okay, so these are the values you are going to calculate. Then calculate COP. And here, how to calculate the power? 5 is energy revolutions for 5 revolutions, 750 energy meter constant, 3600 you are going to convert into joules per second. 98 is the second required to run the compressor. You are getting 0.2448, and in the second case we are getting COP as 4.85. Okay, so 0.2448 divided by 4.85, you are getting 0.06997 kilowatt per hour. Okay, so okay, just today once again you just check it out, HS chart. Okay, that is refrigeration 1 to 2 chart. You take some value and just you find out. Okay, and then find out the COP. Mainly you are going to find out, because taking the readings you can take in 5 minutes, but only to find out H1, H3 and H2, most important. Okay, so one is evaporator temperature and one is a condenser temperature. Okay, Nihar Sai, Nihar.
Yes, sir.
Have understood something? Okay.
Yes, sir.
Okay, how to see the chart? Okay, you have to see the chart, most important. That is called as a refrigeration chart. Okay, you
Yes, sir.
you know how to see this Mollier diagram?
No, sir.
No, you're not studied in thermodynamics, that Mollier chart. Okay.
No, sir.
Okay, just you spend some 5 to 10 minutes. Okay, how to see the pH chart? Okay,
Yes,
just
sir.
you Google it, refrigeration 1-2 chart, and how to see the values of H1, H2, like that. You just you type it, you'll get the information. Okay.
Yes, sir.
Okay. So, and formula is very simple. H1 minus H4 divided by H1 minus H2. Okay, but only two location of points are most important, and conversion factor is most important. Okay.
Yes, sir.
Okay. Okay. Thank you for joining the session, guys. Okay. Shall I share that video, whatever I explained in? Shall I share that link to you, all of you?
Yes, sir.
Okay, I'll share that link so that you can refer that link, and just you click on that link, you'll get the information. Okay, once again, if suppose you are not understood anything now, at least you go through that link, and so you listen carefully. You'll come to know how to locate H1, H2, H3, H4, etc. Okay, I'll share the link in the group. Okay.
Okay.
Okay. Thank you one and all for joining. Okay.
Thanks.